Today I'm going to show you how to create a display timing circuit. This is part of my project of building my own handheld console. Some of you may know the project from my blog posts. The idea is basically to create my own version of the original Game Boy with different hardware and also running an emulator. I've been writing about the emulator part on my blog and you can read all about it if you want to. I'll put the links in the description. But now, let's get started. This is the display I want to use for my handheld console. It's a 4-inch display with a resolution of 480 x 480 pixels. This will allow me to have a pixel-perfect representation of the original Game Boy games, as this is pretty much exactly 3 times the resolution of the original screen. This screen is controlled by this flat wire down here. This is basically a 60-pin connection, so there's a lot of stuff going on here. Let's have a closer look. The most basic thing on this cable is the power supply located here. There's connections for a 12V power supply for the background LED and there's connections for a 3V power supply for the display logic. The rest is split up into 3 different interfaces. Over here is the serial peripheral interface, aka SPI. This is used for sending commands to the display. Commands can be as simple as turn the display on or off, or more complicated like choosing the number of bits used to transmit color information. Which leads us to the RGB interface. The RGB interface has 24 dedicated connections for color informations. These are 24 individual bits for color data. That's 8 bits or 1 byte for each of the base colors red, green and blue. Alternatively, this display can be used in a 16-bit color mode, and that's what I'll be using. That's more than enough for a proper Game Boy emulation and it allows me to save a lot of space in memory as well as physical space for all the connections. The RGB interface also includes connections for timing signals. These ultimately determine the refresh speed of the display and that's what this video is all about. But first, there's a third interface, the MIPI Display Serial Interface. This is a modern high-speed serial interface for commands as well as pixel data. This is an alternative for the combined use of the RGB interface and the SPI. Since I'll be using the latter two, I won't be looking further into the MIPI interface. So let's have a look at all the timing signals we need to generate. First, we need a pixel clock. This is a basic square wave at a constant frequency. Whenever the signal goes high, like this, the display will read the color information on the data connections. With this information, it lights up the next pixel in the row. After the first row is filled up with pixels, we need a horizontal sync signal. The connection for this signal is kept high at 3V until a line is filled with pixels. Then the connection is pulled low to 0V for a short amount of time. This is almost like a line feed or carriage return on an old typewriter. It tells the display to jump to the beginning of the next line. Then pixels are filled in again, paced by the pixel clock. When all the lines have been filled like this, a vertical sync signal is needed to tell the display to jump to the top again. This works exactly like the horizontal sync. The connection is kept high until all the lines are filled. Then the signal is generated by pulling the connection low for a brief amount of time. Additionally, we also need a data-enabled signal. This is kept high whenever we're putting pixels on the display and is pulled low whenever we're outside the visible area. To understand what exactly that means, let's consider this. These are the 480 x 480 pixels. With every rising edge on the pixel clock, a pixel is drawn on the display, one by one, from left to right. When we reach the end of a line, a short amount of time is required before a horizontal sync signal may be generated. This is also called the backporch of the line, because it's the time after each line. Then the H-sync signal is generated. And after that, again, a short amount of time is required before the next line may start. This is called the front porch of the line because it's the time before each new line. Now, the data enabled signal is high while we're on this visible part of the screen, and it's low over here. This determines the duration of the front and back porch. The same concept goes for the vertical sync. After all the lines have been drawn, a short amount of time is required before the V-sync signal may be generated. And also, a short amount of time is required after the V-sync signal. This is the front and back porch of the vertical sync. So, to recap, we need to generate 4 signals: the pixel clock, the H-sync, the V-sync, and the data-enabled signal. Now let's have a look at how this is done. I'm going to sketch out the circuit using this simulation software. We'll start with the pixel clock. For that, we use a signal generator. This will give us a pulsating signal at a constant frequency. Let's use 1 Hz for now. This equals 1 pulse per second. Next, we need to somehow count pixels, because we want to alter our signals after some amount of pixels. For example, we want to know when we reach 480 pixels, because that's 1 line of pixels. After that, we need to set the data-enabled signal low and also generate the H-sync signal. So we need a counter of at least 9 bits. This will allow us to count up to 512. We only need to count to 480 plus the back porch plus the H-sync plus the front porch. Let's see how we can detect when the counter hits 480. 480 is exactly when the topmost 4 bits are high and the bottommost 5 bits are low. So let's take an AND gate with 4 inputs and connect the topmost 4 outputs of the counter. Those of you who have seen Ben Eater's videos on his breadboard graphics card will recognize all of this pretty well. If you haven't seen his videos, I highly recommend them as he is exceptionally good in explaining these things. I'll put the link in the description. So now, as soon as bits 6, 7 and 8 are high, the output of the AND gate will also be high. If we keep counting up, this will stay high, because those upper bits won't change. That's not what we want though. We want to generate a short pulse signaling that we've reached 480. This pulse will be fed into a latch, but we'll come to that later. In order to make sure we really only catch 480, we're going to add another AND gate to make sure that the lower 4 bits are low or 0 when this line goes high. Now feeding 4 zeros into this AND won't do us any good. We need to invert the signals for it to work as intended. So let's add 4 inverters. This just takes zeros and make them ones. Likewise, they take ones and make them zeros. So we've got 4 ones going into this AND gate whenever these lower bits are 0. Let's connect the outputs of these AND gates to a NAND gate. This will give us a constant 1 or high on the NAND's output. Except whenever the counter hits 480, the NAND gate will output a short pulse by briefly going low. This is exactly what we wanted. Let's create a latch now to feed this pulse into. We create an SR latch using 2 NAND gates. This latch is going to have a stable output that can be influenced by pulses at its 2 inputs. That's perfect for our data-enabled signal. We want to have this signal high until we reach 480 pixels. Then the signal should go low and stay low until a new line starts. With an SR latch, we can control this signal by 2 short pulses, one at the count of 480 and one at the count of 0 or 486, because that's when we'll be resetting the counter to 0. This will give us enough time to also generate the H-sync pulse somewhere in between 480 and 486. We already have our first input to the latch, the one that sets the signal low. Now we need another input to set the signal high again. For that we're going to take the output of this one AND gate and feed it into another NAND with 3 inputs. The first input will be high whenever the counter is at 480 or higher. In order to make sure we only catch 486, we take the outputs of the counter at bit 2 and 3 and feed them into the NAND. Bit 2 and 3 are high at the count of 6. Together with 480, we get a total count of 486. So let's feed that into the other input of the latch, and we got ourselves a data-enabled signal. There's only one thing left to do now, and that's taking the output of the NAND gate signaling the count of 486 and feeding it into the reset input of the counter. This will make sure that the counter is reset at the count of 486. We now have a generator for the data-enabled signal, and we can actually see this quite well when simulating the circuit. If we accelerate our pixel clock and watch its output together with the output of the latch, we see that the signal seems to be working as intended. It stays high most of the time and goes low just for a few clock cycles. Now we still need an H-sync signal. We're going to generate this at the count of 482. This will give us a backporch of 2 clock cycles. Let's take another NAND gate and hook up the output of bit 2 and the inverted output of bit 3, as well as the output of the 480 detecting AND gate. This will give us a short pulse at the count of 482 that should last for 2 clock cycles. Let's check the measurements. As you can see, the H-sync signal is generated right in the middle of the data-enabled signal. This should provide for a proper front and back porch between the lines. And that's basically it. For the V-sync, it's exactly the same, only at the count of each line instead of each pixel. And this is how it looks in real hardware. That's exactly the circuit we just designed. With this chip being the counter, this one housing 6 individual inverters, and this 2 4-input AND gates, these 2 NAND gates, and this over here for 2 input NAND gates. Now let's take the exact same circuit again and feed the line reset output from the first one into the counter from the second one. And we've got the exact same thing again for lines instead of pixels. All we need now is some constant signal generator, and we also need to combine the outputs of the 2 data-enabled outputs, and our display timing circuit is complete. I've got a 10 MHz oscillator here fed into another counter, so I'll be able to divide that 10 MHz if I want to. As of now, I've got that 10 MHz divided down to 5 MHz. Those 5 MHz will be the pixel clock. If we calculate the vertical sync from this, we get the screen refresh rate. With a 5 MHz pixel clock, the refresh rate of the screen will be around 20 Hz. This is good enough for breadboard prototyping. Let's do some measurements. Using the oscilloscope, we can see our pixel clock clocking at 5 MHz. The signal is somewhat noisy, but it's quite alright for breadboard prototyping. We can also see the H-sync in the middle of the low period of the data-enabled signal. So far, it seems to be working as intended. Now let's hook up a display. I've hooked up my display using some additional circuitry. This here converts my 5 volt timing signals down to 3 volts. And over here I need some SPI input to properly initialize the display. All the color data is connected here in the middle, and it's currently hardwired to a blue color. If it all works, we should see a blue color when powering it all up. And sure enough, we see a screen filled with blue color. That about wraps it up for my display timing circuit. Next, I'll be looking into how to actually get meaningful content to display on the screen. Thanks for watching and let me know what you think of this project.